Hi and welcome back. In this video we will talk about Word2vec approach for texts, and then we will discuss feature extraction for images. After we summarized pipeline for feature extraction with bag of words approach in the previous video, let's overview another approach which is widely known as Word2vec. Just as with the bag of words approach, we want to get vector representations of words and texts, but now more concise than before. Word2vec is doing exactly that. It converts each word to some vector in some sophisticated space, which usually have several hundred dimensions. To learn the word embedding, Word2vec uses nearby words. Basically, different words which often are used in the same context will be very close in this vector representation, which of course will benefit our models. Furthermore, there are some prominent examples showing that we can apply basic operations like addition and subtraction on these vectors and expect result of such operations to be interpretable. You should already have seen this example by now somewhere. Basically, if we calculate differences between the vectors of words queen and king, and differences between vectors of words woman and man, we will find that these differences are very similar to each other. And if we try to see this from another perspective and subtract the vector of woman from the vector of king and then add the vector of man, we will pretty much get the vector of the word queen. Think about it for a moment. This is a fascinating fact, and indeed, creation of Word2vec approach led to many extensive and far-reaching results in the field. There are several implementations of this embedding approach besides Word2vec, namely GLOV, which stands for Global Vector for Word Representation, FastText, and few others. Complications may occur if we need to derive vectors not for words, but for sentences. Here we may take different approaches. For example, we can calculate mean or sum of words vectors, or we can choose another way and go with special models like Doc2vec. Choice of the way to proceed here depends on the particular situation. Usually it is better to check both approaches and select the best. Training of Word2vec can take quite a long time, and if you work with texts of some common origin, you may find useful pre-trained models on the internet, for example, ones which were trained on Wikipedia. Otherwise, remember that training of Word2vec doesn't require target values from your task, it only requires text to extract context for each word. Note that all pre-processing we have discussed earlier, namely lowercase, stemming, lemmatization, and usage of stop words, can be applied to text before training Word2vec models. Now we are ready to summarize difference between bag of words and Word2vec approaches in the context of competition. With bag of words, vectors are quite large, but as a nice benefit, meaning of each value in the vector is known. With Word2vec, vectors have relatively small length, but values in a vector can be interpreted only in some cases, which sometimes can be seen as a downside. The other advantage of Word2vec that is crucial in competitions is that words with similar meanings will have similar vector representations. Usually, both bag of words and Word2vec approaches give quite different results and can be used together in your solution. Let's proceed to images now. Similar to the Word2vec for words, convolutional neural networks can give us compressed representation for an image. Let me provide you a quick explanation. When we calculate network output for the image, besides getting output on the last layer, we also have outputs from inner layers. Here we will call these outputs descriptors. Descriptors from later layers are better to solve tasks similar to one network was trained on. In contrary, descriptors from early layers have more task-independent information. For example, if your network was trained on ImageNet dataset, you may successfully use its last layer representation in some car model classification task. But if you want to use your network in some medical specific task, you probably will do better if you if you will use an earlier full connected layer or even retrain network from scratch. Here you may look for a pre-trained model which was trained on data similar to what you have in the exact competition. Sometimes we can slightly tune network to receive more suitable representations using target values associated with our images. In general, process of pre-trained model tuning is called fine-tuning. As in the previous example, when we are solving some medical specific task, we can fine-tune VGG, ResNet or any other pre-trained network and specify it to solve this particular task. Fine-tuning, especially for small datasets, is usually better than training standalone model on descriptors or retraining network from scratch. The intuition here is pretty straightforward. On the one hand, fine-tuning is better than training standalone model on descriptors, because it allows to tune all network's parameters and thus extract more effective image representations. On the other hand, fine-tuning is better than training network from scratch if we have too little data, or if the task we are solving is similar to the task model was trained on. In this case, model can use domain knowledge already encoded in network's parameters, which can lead to better results and to faster retraining procedure. Let's discuss most often scenario of using the fine-tuning on the online stage of the Data Science Game 2016. The task was to classify satellite photos of roofs into one of 4 categories. As usual, log loss was chosen to be the metric. Competitors had 8,000 different images. In this setting, it was a good choice to modify some pre-trained network to predict probabilities for these 4 classes and fine-tune it. Let's take a look at VGG16 architecture. Because it was trained on 1000 classes from ImageNet, it has output of size 1000. We have only 4 classes in our task, so we can remove the last layer with size of 1000 and put in its place a new one with size of 4. Then we just retrain our model with a very small learning rate, usually about 1000 times lesser than an initial learning rate. Great, that is, fine-tuning is done. But, as we already discussed earlier in this video, we can benefit from using model pre-trained on the similar dataset. ImageNet by itself consists of very different classes, from animals to cars, from furniture to food. Could we find more suitable pre-trained model? Indeed, we just could take model trained on places dataset with pictures of buildings and houses, fine-tune this model and further improve the result. If you are interested in details of fine-tuning, you can find information about it in almost every neural networks library, namely Keras, PyTorch, Caffe or other. Sometimes you also want to increase number of training images to train a better network. In that case, image augmentation may be of help. Let's illustrate this concept of image augmentation on the previous example with classification of roof images. For simplicity, let's imagine that we now have only 4 images, one for each class. To increase the number of training samples, let's start with rotating images by 180 degrees. Note that after such rotation, image of class 1 again belongs to this class, because the roof on the new image also has north-south orientation. Easy to see that the same is true for other classes. Great! After doing just one rotation, we already increased the amount of our trained data twice. Now, what will happen if we rotate image from the first class by 90 degrees? What class will it belong to? Yep, it will belong to the second class. And eventually, if we rotate images from the third and the fourth classes by 90 degrees, they will stay in the same class. Look, we just increased the size of our trained set 4 times. Although adding such augmentations isn't so effective as adding brand new images to the trained set, this is still very useful and can boost your score significantly. In general case, augmentation of images can include crops, rotations, adding noise, and so on. Overall, this reduces overfitting and allows you to train more robust models with better results. One last note about extracting vectors from images, and this note is an important one. If you want to fine-tune convolutional neural network or train it from scratch, you usually will need to use labels from images in the train set, so be careful with validation here and do not overfit. Well done! Let's recall main points we have discussed here. Sometimes you have a competition with texts or images as additional data. In this case, you usually want to extract useful features from them to improve your model. When you work with texts, pre-processing can prove to be useful. This pre-processing can include lowercase, stemming, lemmatization, and removing stop words. After the pre-processing is done, you can go with either back-of-words or with Word2vec approach. Back-of-words guarantees you clear interpretation, each feature achieved by means of having a huge amount of features, one for each unique word. On the other side, Word2vec produces relatively small vectors, but meaning of each feature value can be hazy. The other advantage of Word2vec that is crucial in competitions is that words with similar meaning will have similar vector representation. Also, n-grams can be applied to include words interactions for texts, and TF-IDF can be applied to post-process metrics produced by back-of-words. Now, images. For images, we can use pre-trained convolutional neural networks to extract features. Depending on the similarity between the competition data and the data network was trained on, we may want to calculate descriptors from different layers. Often, fine-tuning of neural network can help improve quality of the descriptors. For the purpose of effective fine-tuning, we may want to augment our data. Also, fine-tuning and data augmentation are often used in competitions where we have no other data except images. Besides, there are a number of pre-trained models for convolutional neural networks and Word2vec on the internet. Great! Now you know how to handle competitions with additional data like texts and images. By applying and adapting ideas we have discussed, you will be able to gain an edge in this kind of setting.